Hello everyone. I'm going to discuss about minimization techniques. Before that, let me introduce myself. I am A. Satya Abhinay and I'm from EC branch. My roll number is 403. Let's go into the topic. Let us see the outline of this presentation. First, we will discuss about the minimization in decisional logics, why we need the minimizations, and the reason behind it. Now and then we will discuss about Boolean simplification principles, the principles we are going to use, and the methods of minimizations. And in those methods, we will discuss two of them. There are algebraic method with and K-map method with some examples. And then we'll see the applications to the minimization techniques, and then we'll conclude the session. Let's start the topic. The minimization of the logic expressions. Why we need the minimization? Using the number of logic gates and inputs needed without changing the output behavior. We need to decrease the size of the chips we are going to use in the devices so that it does not weigh so much and it does not occupy much space. So we use minimization techniques in order to decrease the number of gates. After doing the minimization, we will get a smaller circuits which are cheaper, faster, and more reliable, and which consumes less power. How we will minimize the logic expressions? What is the method behind it? That is identifying and removing redundant terms and inputs in Boolean expressions that doesn't affect the output. We need to minimize the logic expressions by using some logics so that our output will be the same, but the input will be the change. So the example is two different Boolean expressions or circuits can produce the same output, but one with fewer gates and preferred. The methods we are going to use in this minimization are algebraic method, K-map method, and Quine-Mikulski method. In these methods, we'll be discussing about algebraic simplification and Karnaugh maps with some and then we will discuss about the importance. The minimization improves the efficiency of digital system design, impacting hardware cost, speed, and power consumption. So let us go to the next slide. We will discuss about the Boolean algebra foundation minimization. Boolean algebra is the main foundation for the minimization. In order to minimize a logic function, we use Boolean algebra. Boolean algebra simplifies the digital logic expressions, essential for designing efficient digital circuits. In this, we use logical operators such as AND, OR, NOT, NAND, etc. It helps us to reduce the circuit complexity, cost, and power consumption. It also increases the underpins methods like Karnaugh maps and Quine-Mikulski and algebraic method too. Fundamental in digital electronics and computer science. This means Boolean algebra is the very foundation for the fundamental in digital electronics and computer science. By understanding this, we will be getting a strong foundation for digital electronics. Coming to the next slide, methods of minimization. There are three types of methods. One is algebraic method, Karnaugh map, and Quine-Mikulski tabular method. Algebraic method uses Boolean laws and theorems to manually simplify expressions, whereas Karnaugh maps uses visual method using a grid to group adjacent ones use efficient for up to 4 to 5 variables. And we will look into that in upcoming slides. We will discuss about the algebraic method for minimization. In this algebraic method, we use Boolean laws and theorems to simplify expressions. It is a manual process so that we do not have any particular logic that we need to use, but we need to have some common sense and presence of mind in order to find the logic and minimize terms in the given functions. There are no fixed rules, and it is very effective for simple or small Boolean functions. When we are given a simple or small Boolean function, we can use algebraic method in order to solve it very quickly and easily. But when the variables in the functions increase, we need to go for the other methods such as Karnaugh maps, etc. Algebraic method involves identity, null, complement, distributive, and De Morgan's theorem. It results in reduced number of terms and simpler expressions, which is the goal. Let us discuss an example for that. Let us consider a function f equal to b of a plus c plus ab complement plus bc complement plus c. Now, in order to solve this, we need to expand the brackets by multiplying the outside term with the terms which are inside. We will get f equal to ab plus bc plus ab complement plus bc complement plus c. Let us rearrange that and group similar terms so that we will get AB plus AB bar in which A is A of B plus B bar, which in we know that B plus B complement is equal to 1, so that A into 1 becomes A. We simplified the first step group. Now let us go to the next group. BC plus BC complement. In this, B is the common term. Let us take that common. And as we know, C plus C complement results in 1. So C into 1 gives C. Now the result from the given function, which is minimized, is f equal to a plus b plus c. Here we need to understand that the given function and the solved function both results in the same input. Let's go to the next slide. In this slide, we will discuss about K-map method, which is known as Carnot map. Carnot map uses visual grid techniques for simplifying Boolean expressions. It organizes truth table outputs into a map for grouping. It is also effective for functions up to 4 to 5 variables. Unlike the algebraic method, which is used for simplified functions, we use Carnot map for a bit more complex functions, which contains up to 4 to 5 variables. It groups the adjacent ones to minimize the logic. It eliminates the need for lengthy algebraic manipulations. Before using the K-map, we will get a long function with so many terms. And after using this with some particular logic of combining ones, we will decrease the we will minimize the terms in it and we will get a simpler output. Solution can be in sum of products or sums form. So it can be both in both of the forms. Let us discuss the rules for the K-map. Let us select K-map based on the number of variables. It may be 2 by 2, 2 by 4, or 4 table. So from the function, let us fill the cells with 1 if they are sum of products, and let us fill a table with zeros if they are product of sums. It will be depending on the input function. Based on the truth table, adjacent ones or zeros strictly in powers of 2. That means 2 power 0, 1, 2 power 2, 4, 2 power 4, etc. 2 power 16, etc. so on. It has to be in these grouping. Groups must be rectangular. Groups must be rectangular form. And the diagonals are forbidden. So groups can overlap and wrap around edges. While grouping, one group may overlap with another group. It is a no problem. So everyone should be included in at least one group. Maximize group size for greater simplification. Before getting the logic, we need to assure that the groups we are assigning will be up to the maximum size. If it contains 16 or a 8-bit, we need to choose 16 because it has a greater size and it will result in simplification, greater simplification. Let's discuss an example to understand it better. Let us consider a function f equal to a, b, c, d. That means we have the 4 variables a, b, c, d, and it is equal to a, b complement, c complement plus ac plus a complement, c, d complement. We write down the given Boolean function in terms of 4 variables, which we did, and then we convert each product term into its corresponding min terms. The specific cell positions in the K-map. As you can see, A, B complement, C complement, its minterms are 8, 9, and you can see the following. So, since these are sum of products, we will use ones in the tables by using the minterms. We will fill the table with the minterms at their respective positions. As you can see in the table, we filled these, and after that, identify the largest possible groups of ones. It may be 2, 4, or 8, but take as big as possible. Make sure to wrap them regardless of the overlapping. From each group, determine the simplified product term. By grouping them, we need to simplify product, and we need to convert all the essential groups to ensure every midterm is covered. Combine these simplified terms to product to form the minimized Boolean function. After getting all these terms from the table, we need to combine them so that we will get the output, which is a simplified version of the given input. So we will get an output f equal to AB complement plus AC plus CD complement. It may differ from the given function, but it gives a simple input. Next, we will discuss the applications of the minimization techniques. So it is used to reduce hardware complexity. As we discussed before, minimization techniques are used to decrease the complexity used in the circuit functions. It decreases the number of logic gates we use in the circuits. It simplifies the design, lower cost by using after and it improves performance. The efficiency of these devices which are made by minimization techniques will be more compared to the uh, ones which are not minimized with any logic. And it also decreases the power consumption. After using minimization techniques, or less power usage, which results in less power consumption. So it also enhances the reliability. It also enhances the lifespan of the devices. Reduced circuit complexity means fewer points of failure and easier debugging. And finally, it is used in many applications and many devices such as microprocessor, memory systems, business signal processing, etc. We will conclude the session by discussing the summary of what we discussed in this presentation. The minimization reduces complexity of digital logic circuits, which we discussed. It is covered. Boolean algebra provides the foundation for simplification. It is also covered. Algebraic method and K-map are effective minimization techniques. We discussed them with some examples to understand very easily. Simplified circuit result in lower cost, lower power consumption, and faster operation. And we discussed this also. Minimization improves reliability and ease of maintenance. We discussed all of these points in the applications slide. Thank you all, and thank you for the time you spent for listening this presentation. Thank you.